All right, so good evening. Today we'll go over the 2022 exam 3. One thing, I don't think this exam, I don't think it has Kleisen condensation, and that won't be on your exam on Friday anyway. So, I don't think I have any questions on this exam on it. Yeah, if I do, I'll let you guys know. All right, so we'll start with the nomenclature. Um, First thing, uh, we have this hexene ring, right? And it has a nitrile group, CN, and the CHO. So that's an aldehyde. So if we're gonna draw these out, this would be a oh, this would be a wedge onto a C triple bond N. This would be a wedge onto a C with a double bond O onto an H. So we have an aldehyde and we have a nitrile, right? So between these two groups, the nitrile is actually the one that is going to take priority over the aldehyde. So because of that, we'll start numbering from the nitrile. So that'll be our number one. So we'll count it both ways. So 1, 2, 3, 4, 5, 6. And then also the other way, count it 1, 2, 3, 4, 5, and 6. So with the blue numbering, we have our substituents on carbons 3 and carbon 4. So the double bond is considered a substituent here. And then on with the black numbering, we have our substituents on carbon 3 and carbon 5, right? So the best case, we're going to be using the blue numbering. All right. So we'll start with the blue numbering. We'll start with the parent chain, right? So the parent chain is a cyclohexene. So cyclohexene. And then we're going to add the nitrile into the parent name. So whenever we have a nitrile just regularly on a regular chain like this, right? Just a regular chain, this would be called just a nitrile, right? We would add the nitrile to the end of it. So if this is a 1, 2, 3, 4 carbon chain, so we would have a butane nitrile. But because this is a cyclo, it's not gonna follow those same naming standards. Instead, we're gonna have the cyclohexene. We're gonna add the E, but then we're also gonna call it a carbonitrile. So carbonitrile, and this is only whenever the parent chain has the nitrile group and it's part of a ring structure, right? So because we have that, this is going to be our full parent chain. We don't have to indicate that which carbon the carbonitrile is on because it's already assumed number one. And then the cyclohexane, we do have to show where the double bond is. So according to our numbering, it's on carbon 4. So we'll start with that. 4 cyclohexene carbonitrile, right? And then for our substituents, so the only substituent that we have is this aldehyde. And because it's not in the parent chain, for example, if it was in the parent chain, we would call it xenal. I guess we wouldn't have it with the nitrile, but if let's say the nitrile wasn't there, it would be cyclohexenal, right? To show that it has an aldehyde on it. Because it's a substituent instead this time, it's not going to be part of the parent chain name. As a substituent, it's going to be called the formal group, FORMYL. For example, you know formaldehyde. See, it's the same thing. Formal, you just call it like that if it's an aldehyde there. Formaldehyde, formal, right? So that's our substituent. It's going to be on 3. So 3 formal. And then we do have also stereochemistry. So whenever we look at the stereochemistry, the double bond is not going to count in this case because we already have, it's part of a ring structure and both of those have hydrogens on it. So we're not going to be worrying about the double bond. Um, However, these both are on wedges, and whenever they're both on wedges on a whenever two things are on the same thing on a cyclo, I guess. So let's say they're both on a wedge or both on a dash, right? then this would be cis. But if there were one is on a wedge and one is on a dash, then this would be trans, right? And because both of these are on a wedge, this would be our stereo would be cis, right? So now we've done everything and we can put it all together. Cis dash 3 dash formal dash 4 dash cyclohexene. And remember, whenever you're naming this, to keep it in one word, it gets a little bit long, but the carbonitrile is also part of the one word. So cyclohexene, we're going to keep the E and then add carbonitrile. So carbonitrile. And we can also say 3-formal cyclohex dash 4-ene carbonitrile. Right. So both of those work. Any questions on the first problem? Yeah. Yes. You had a question as well?
Back to your linear, does the carbon that's part of the nitrile get counted in?
No, it doesn't. Yeah. So the carbon that's part of the nitrile does not get counted. It's a good point. Yeah. For the linear, I don't think it counts for the linear, does it? Do you guys know? It does? Okay. Then I guess this would be a pentane nitrile. I appreciate that. I guess I didn't know. Thank you. Any other questions? All right. So on to the next one. So over here we have an amide, right? So this structure is called an amide. So whenever we have an amide, the parent chain is going to be well, it's going to be part of this. According to this molecule, this amide is going to be part of the parent chain, right? I don't know why my. Okay, now it's working. Okay, so the parent chain is part of the amide, or the amide is part of the parent chain, and then we have two substituents coming off of the nitrogen group. Still not working. I don't know why. Okay. So we have two substituents coming out of the nitrogen group, and then we have one substituent coming off of the parent chain, right? So we'll just circle these. So these are going to be our three substituents. Whenever we have an amide, we're going to start numbering from the carbon that's attached to the oxygen of the amide, or I guess the nitrogen as well. It doesn't really matter. They're both the same. So we're going to start with this carbon, right? So we'll start numbering from there. So 1, 2, 3, 4, 5, 6, 7, and 8. So there's a little bit of a different nomenclature that we're going to use to identify that that these groups, these substituents that are connected to the nitrogen are connected to them, just to show. We're not going to use like 1. Instead, the prefix that we're going to use is N. I don't know if prefix is the right word, but if I went to substituents, we're going to have N, right? And then we have 1, 2, 3, 4. So this is a butyl group. And 1, 2, 3, 4, 2. So two butyl groups, right? So in this case, we have to put N comma N and then dibutyl because we have two butyl groups. And we're not going to say that it's on one N or like 2N, right? This is just saying that it's connected to the nitrogen. So N dibutyl. And you do have to put both N's. If you just put N dibutyl, then it, I don't know, but I'm pretty sure you can't do that. And then, so from that, and then we also have the other sub. So on number 5, we have a phenyl group. So 5-phenyl. Remember that the phenyl is just the benzene group, right, like this. And the benzyl group is the one with the CH2 between it. So because this just has the group right here, the benzene, we're just going to call it a phenyl, right? And then that's everything that we need now in terms of substituents. And now to name the parent chain. So the parent chain is going to be an octane, right? So we have the octane, but then we're going to add amide because this is an amide, right? So octane, AMIDE. So in this one, we are going to be getting rid of the E for the octane. So we have octanamide, and we don't have to identify which number the amide is on because it's already assumed that it's on carbon 1. So whenever we put it all together, we'll use the same structure as before. We're going to go by alphabetical order. So butyl comes before phenol. So we're going to start with the NN dibutyl. So N comma N dibutyl, and then 5-phenol dash 5 dash phenol, and then we'll add octanamide. Right. So any questions on this second problem? Yeah. 1-oxo. So you wouldn't be able to do 1-oxo because this is the oxo just tells you that it has a ketone there, right? And so because this is an amide rather than a ketone, right? It's a little bit it's gonna have a different naming. That makes sense. Any other questions? All right. So third question. So this is a keto ester. So okay, nice. So we have a cyano group right here. But the cyano group is actually not going to be our, well, I kind of, never mind. The nitrile group is not going to be our parent chain. Instead, it's going to be this ester, right? So esters are have a higher priority than nitriles. So if you were to go about it, it would be aldehydes, ketones, then aldehydes, then nitriles, then esters, right? Esters are going to be your highest priority. And so now, whenever we look at this, the naming of esters is a little bit different. I think I said this in like a different exam review. I don't remember. But we're actually going to use two different words in this one. So whenever we put a space in this, especially for esters, it's very important that you leave a space in between of the naming. And I'll show you why that's important, right? So the side that doesn't have the oxygen on it is going to be, or the ester oxygen on it is going to be our parent chain. So we'll start with this numbering. So number 1, 2, 3, and 4. And so that's going to be our butane parent chain. So our parent chain is going to be a butane. We'll leave the naming for the ester for a little bit later. So right now, let's just call it a butane. And so we'll start with the substituents. So substituents, we have on carbon 3, we have an oxo group. And then on the other side, we don't have any other substituents on the left side. But on the other side, on carbon 1, we have a nitrile group. So whenever we have a nitrile group, it's not going to be called a nitrile as a substituent. We're going to call it a cyano group. So another sub that we have is 1-cyano, right? And so now we don't have any we don't have any stereochemistry. So now we can finish naming the parent chain. So we know that it's a butane, right? But the naming convention for esters, we're going to change butane. We're going to drop the E and add O8, right? So butane O8E, right? So that's going to tell us that we have an ester, right? And the ester is already assumed on carbon 1, so we're not going to say anything. So if we put it all together, we're going to have we're going to start by naming the oxygen side, right? This side over here, this substituent. So we're going to start with 1-cyano. cyano, and then this is a 3-carbon chain, 1 cyanopropyl. I probably should have, right? So we have the 1 cyanopropyl, and now we're gonna have a space. So whenever we have a space, we're essentially indicating that this is the one side of the ester, and now we're gonna start naming the other side of the ester. So we're gonna leave a space here. I'll just put this right here just to indicate that we have a space. So we have a space, and then we put our substituent and then the parent right after, right? So we have a 3-oxobutanoate on the left side. So that we're not gonna put a dash here, even though I put one there. So because we have a space, we don't need to put a dash. So we put 3-oxobutanoate. And that will be, yeah, that will be the complete name for our compound. And yeah, if you put a dash in front of the 3, they're gonna assume that it's gonna be in the same word. And so if you actually had a dash there, the 3-oxobutanoate, that would like be assuming that we had like an oxygen right here, right? And so you need to have that space there to show that the oxygen is actually on the other side of the ester, right? Any other questions? All right. So we'll get into the facts section. So place the compounds in order of increasing reactivity with H3O plus, 1 for the least reactive and 3 for the most reactive. So whenever we have reactivity with H3O plus, in this case, we're gonna have a cleavage reaction that's gonna occur in between the ester right over here. So whenever we have that, we're gonna have this oxygen with a minus charge, right? So if that was to happen, so this oxygen is gonna have a minus charge that's going to want to bond with the one of the H's and become an OH, right? But now we have 3 different compounds that we can consider, right? So what we're gonna do, we're only gonna consider the part that's leaving, right? So if we assume that the ester is part of the original compound, right? This ester is the original compound right here. So everything to the right side, let's consider it the original compound, and then everything that's leaving, we'll consider it leaving. And we'll only focus on the leaving group. So we see those benzenes in the double bond oxygen. We don't care about that. We just look at the leaving group. So we'll look at the leaving group, right? So on this first one, we have an electron donating group, the CH3. So this is an electron donating group by induction, right? This NO2 right here is an electron withdrawing group by resonance. And then this OCH3 right here is an electron donating group by resonance. Okay. So what do we know about electron donating groups? What electron donating groups like to do is that they like to make this minus charge on this oxygen become more negative, right? So let's say that this oxygen started donating more electrons over here. It would make this oxygen a bigger negative, right? And what does that do? It causes it to become more unstable, right? And we do not want unstable leaving groups. We want stable leaving groups, right? So for example, this NO2 is going to be pulling a lot of electron density from that minus charge. And so because of that, it's going to become a better leaving group because it's going to be more stable after it leaves, right? So if we look at it from this way, an electron donating group is going to increase it. So electron donating groups in this case are bad. So EDG equals bad and EWG equals good. Okay, so we want electron withdrawing groups. So because of that, this electron withdrawing group is going to be our most reactive because it creates the best leaving group. And now we have an electron donating group by induction and by resonance. So because the one that's because the electron donating group by resonance is going to be stronger, is going to cause that minus charge on that oxygen to become bigger, and so it's less stable than the one from induction. So because of that, this right side is going to be the least reactive, and the CH3 is going to be our second most reactive in this problem. Any questions on that? I got that answer. All right. So now place the compounds in order of increasing acidity. So this is a little bit of a different kind of way that I'm going to solve this problem. Usually I solve the acidity problem just by like resonance because I think that's what happens. But in this case, we can't really use resonance because it kind of just like keeps going and going. And all of them have like pretty nice resonance structures. Like you go over here, you go all the way around, right? So we won't go by resonance this time. Instead, this time we're going to go like I guess the textbook way. So first we're going to get rid of the most acidic hydrogen. So rid of most acidic hydrogen. So in this case, we have two options. We have this NH and then we have the carboxylic acid, right? And it's literally in the name. We want to get rid of that carboxylic acid's hydrogen, right? So what that's going to look like now is going to be like this. And then we're going to have minus here, right? So now whenever we look at this problem, we'll have the CO2 minus instead of the CO2H. And now we'll look at the groups that are close to the negative charge, right? So we have an amine, we have an amide, we have an amide, and we have another amide. All right. So let's look at them all separately. Here we go. So let's start with the amine. Okay. So this amine is this one is an electron donating group by resonance. Okay. We'll just look at it like that. Electron donating group by resonance. This the amide in itself is an electron donating electron withdrawing group, but this we'll look at this amine for now, I guess, the NH. So we'll call this an electron donating group. And but however, this electron donating group is going to be donating electrons both ways, right? It's going to be donating towards that oxygen and towards the CO2 minus. This is only going to be donating in one way. So this is a stronger one, and this is a weaker one, right? So we're looking at the NH because that's where the hydrogen is attached to. So we're looking at where the hydrogens are attached so that we can find where the how the electrons flow. So this NH, this one is going to be blocked a little bit because of this amide. So this entire thing, we'll just call it an electron withdrawing group, right? And so whenever we have increasing acidity, we want something to be more stable, right? So a higher state, a compound that's more stable is going to have a lower negative charge because it's going to be so it's going to have a lower negative charge, right? So it's going to be what's it? The negative charge is going to be distributed across the compound like in a more even fashion, right? So if we look at this electron donating group by resonance, right? What's going to happen to that minus charge? That those electrons are going to be donated and then the minus charge is going to get bigger in size. And it's going to be by resonance, so we already know it's strong, right? So this is going to be a very like what's it? Very unstable atom because that minus charge is just getting bigger and bigger, right? And then on this one, we have an electron donating group. And even though it's getting pulled two ways, it's still going to be increasing the minus charge by a little bit, right? So that minus charge will still increase. So it's not like too unstable, but it's not necessarily stable either, right? So slightly stable. And then our third one, we have an electron withdrawing group. And what's the electron withdrawing group going to do? It's going to pull that minus charge over, right? And because of that, that minus charge is just it's gonna become dissociated across the entire compound. And So as a result, we have our ranking already. So the most acidic is going to be the most stable one. So 3. Least acidic is going to be the one that's the most unstable. 1, and the other one is 2. Any questions on how I got that? Yeah, one more time. Yeah, it would depend on the question because okay, so for example, in this question, it was asking in reactivity with H3O plus. I don't know what else they could ask, but in a different reaction, it could flip them, right? Yeah, just pay attention, right? Like this could have easily been a resonance question as well, like you guys have seen on the other exams. It's just that this one had a, I guess a different flair. You know, you maybe this maybe in a different exam you would have the amine, it would lose its hydrogen there, and then you would do it differently. I think in the amide's case it would be the same thing, but you know you just have to be prepared. It's not going to be exactly like how it's shown here, right? Any other questions? All right. So place the compounds in order of the amount of hydrate formed in NaOH. All right. So the amount of hydrate formed in NaOH. Uh, okay. So in this one, we have uh so all on all of these problems, we focused on one singular part of it, right? On the first problem, we focused on the leaving group. Second problem, we focused on the electron donating groups, withdrawing groups, right? This problem is very similar to that. So whenever we're having a reaction with NaOH in this context with the ketone and what we've learned, we're gonna be looking at alpha carbon. I think alpha carbon. What's it? Charge, the charge of the alpha carbon, right? And so what that means is that we have a ketone in every single one of these, right? And so now we can find out with the alpha carbon, the charge, how it will be affected. So we'll look at this middle carbon right here. So this is the most important carbon that we want to look at. All right, so let's focus there. So the first carbon, it's near, and so these carbons are supposed to be partially positive, right? So these are all partially positive. So let's determine which ones are going to be the most partially positive. Okay. So this one, this OH is an electron withdrawing group, and this is an electron withdrawing group by resonance. Okay. So what that means is that this delta positive charge is going to go away from it and it's become a smaller delta positive charge, right? And so we'll talk about how that affects the amount of hydrate formed. Essentially, what this is asking is which one is going to react the best, right? And the one that's going to react the best is going to be the most unstable, right? The most unstable is going to have the highest partially positive charge, right? So this one, this oxygen, this ether is going to be an electron withdrawing group or donating group, sorry. So this is an electron donating group. Give me 1 second. No, this would be an withdrawing group. So this is an electron withdrawing group by resonance as well. We have the lone pairs, and then this can go over here. This would be an electron withdrawing group. And then we have on this side, we have the electron donating group by induction. So whenever we have an electron donating group, what it's going to do is that it's going to cause the partially positive charge to decrease, right? So this partially positive charge will become smaller. And whenever you have an electron withdrawing group, the partially positive charge is going to increase, right? And whenever we have that increase, we're going to have more hydrate formed. Whenever we have a decrease, we're going to have less hydrate formed. So immediately we have two electron withdrawing groups and one donating group. So that donating group will take it out. So this donating group is going to be our least reactive. Excuse me. I don't know why it became blue. Okay, this electron donating group is going to be our least reactive. Because whenever electrons are donated, the partially positive is going to decrease. Same way, this electron withdrawing group by resonance. This is very close compared to this OH, right? It's literally the next carbon over. So because of that, this one is going to be our most reactive, and this is going to be our second most reactive, the very first one, because even though it's electron withdrawing by resonance, technically, it is one carbon away rather than having anything like, for example, this is like directly connected to the carbon, the oxygen. So it's going to be more powerful. Any questions on that? Which one? Oh, the first. Yeah, technically, yeah, it'd be by both, but I just assume by resonance because of the lone pair. But yeah, it would be by resonance and by induction because of because it has that one carbon split in the middle. You're right about that. Any other questions? All right. Guess we'll go to the next one. So place the compounds in order of increasing acidity. We're gonna go by the same thing this time. We're gonna go by what's it? The stability, right? And we're gonna do something very similar to what we had above, right? So we have beta keto, we have beta keto esters, beta keto amide, and beta keto ketones. Or I don't know the terminology for this. It's not an anhydride, but I forgot what it was. Anyways, so right. So we're gonna look at the middle carbon right here, right? So whenever we have acidity, especially in this exam, one thing we really need to do is deprotonate. Um, deprotonate most acidic hydrogen, right? And this carbon that's in the middle of these two oxygens is going to be having very acidic hydrogens, right, that are attached to it. So this hydrogen, and this hydrogen are all very acidic. So in this case, we're going to deprotonate all of these carbons right here. So those central carbons, we'll start with this one. So we'll just put it like this. Actually, I'll put it below that. And then we'll put a minus charge above. Right. Okay. So we know that the only parts that are changing on this problem are on the right side, right? So we'll look at the right side and we'll determine how the stability is affected, right? So let's just write down a note. So the greater negative charge is a lower stability, and the less negative charge is more stability, right? So let's look at these. So right now we have an ester, an amide, and we have the ketone. So connected to the ketone, we just have these carbons, right? And so these carbons are electron donating groups by induction. So we'll just start with that. So we have the electron donating groups by induction, and now we have two electron withdrawing groups. And both amides and esters are very strong electron withdrawing groups. So we have to decide which one is going to be our which one is going to win, right? Which one is going to be the better electron withdrawing group, right? So whenever something is electron withdrawing, that means it's going to have a higher affinity affinity for their electrons. And so that's essentially saying that a more electronegativity leads to better electron withdrawing group, right? Better EWG. So between these, the electron that the compound that withdraws more is going to be the ester, because the oxygen is more electronegative than nitrogen, and so it's going to pull more of that minus charge over to stabilize the compound. So because the oxygen is more electronegative, this is going to be a greater stability, more stable, and less stable. So because of that, our most acidic is going to be our first one. Our least acidic is going to be the one with the electron donating group, so 2. And then our second most acidic is going to be our amide group. Are there any questions on that? The number one is 3. Wait, do you
Put two.
did I put 2 twos? Oh, I'm so sorry. Yeah, the one on the right is 1. Sorry. I didn't realize I put 2 twos. My bad. Any other questions? So if a compound below will be decarboxylated in H3O plus at 180 degrees Celsius, put Y in the box if it will not put N. So this one is this one we're looking at the alpha beta position, right? So we have we have in this case 2 carboxylic acids, we have the ester and we have a ketone, and then we have 2 esters. Right. So essentially we're looking at just alpha beta carboxyl groups, and we're seeing if they will be if they are even in alpha beta, because this H3O plus at 180 degrees Celsius is an alpha beta reaction. Okay. So whenever we look at this, we're gonna start with just any of these groups that are circled, right? So if the group is on if the group gets to the carbon, actually I'll explain it after I put these. Okay, so we'll start with this group, right? So if we put alpha beta, we're not gonna start at this carbon. Okay, we're not gonna start there. We're gonna start at the next carbon over. So we'll call this carbon alpha, and this carbon beta, right? However, it doesn't go all the way to this next carbon. It has to go to all the way to the next carbon. So this is a whatever the third letter is. I forgot what delta. I got. Let's just call it delta. I don't remember the third letter. Is it gamma? Yeah, gamma. I don't know what the symbol is for gamma. Is it like something like this? Yeah. So yeah, so that's our gamma carbon, and so because it's not alpha beta, not alpha beta, it's not going to be decarboxylated. So we'll put a no in the box. And same thing goes over here. We'll start with this CO2 ET. So we'll start with this carbon right here. So we have alpha and we have beta. And notice how on the beta carbon, we have the carboxyl directly connected to the beta carbon. That's exactly what we want. So in this, we will put yes. And same thing on the other side. We're going to, let's go with the right one this time. We'll do alpha right here, and beta is going to be directly connected to the C that's double bonded to the oxygen. So this will also be a yes, and it'll still work the other way. If we focused on this one, we would still have alpha here, and then we would have beta right here. So it works both ways, right? So because of that, we have no, yes, yes. So yeah. Any questions on that? Before? Did I? Oh, 1, 2, 1, 3. Okay. Why is that? Do you know why? Uh-huh.
Structure is going to be fine because that ester oxygen
Mm-hmm.
is not next to, it's on the middle structure that amide, the nitrogen, will be donating toward.
We're splitting it between the esters and amides. We're splitting it like right over here. So like this oxygen would be donating to this one, and this nitrogen would be donating to this. Is that what you're trying to say? So, like for example, okay, sorry. So this will be donating to this one, so it'll be less withdrawing. So the total thing would be less withdrawing. Is that what you're trying to say? Or am I missing it? Because it's okay, got you. Okay. Oh, okay, I think I understand. Okay, my bad. Okay, yeah, I'll redo the problem then. I'll redo the problem. That's my bad, guys. All right, let's try this one more time. All right. Let's forget about that explanation I did before. Okay. So, one slight adjustment. So we have the two carbonyls right there, but let's say we cut them right here. Okay. I'll try to explain it to you guys like the way that I just understood it. So all of these are going to be pulling electron density, right? This electron density is going to be pulled in every single case, right? Now we just have to determine how strong it's going to be pulled. Okay. So this minus charge is going to be pulled in that way. And depending on how strong this complete area is, will determine how strong it'll be pulled, right? So this oxygen is going to be let's consider a donating group. For example, we called an ether a donating group. So an ether is a donating group. So the same way, let's just consider this an ether, right? So this will be donating electron density towards this oxygen or towards this carbon right here, causing it to be partially negative. This will be also donating electron density towards it, which will cause it to be also partially negative. And this will be not donating anything. It'll be by induction, so it's not going to be by resonance, so we won't even worry about this, right? So let's just call this this will be technically the strongest electron withdrawing group, right? Strongest. Because this is not hindered by anything by resonance, it's just only pulling straight from that carbonyl. Now, whenever we look at these, which one is going to be a stronger donating group, the oxygen or the nitrogen, right? This oxygen is going to be more electronegative, right? And because of that, that electronegativity is going to cause it to want to keep its electrons, right? So we'll keep E minus. So because it wants to keep its electrons, it'll be a weaker donating group, right? So it wants to keep its electrons, so it's not going to be giving as much away versus this nitrogen, which is a weaker electronegative atom, which is going to be make it easier to give, right? Because it's going to be easier to give, it's going to be giving the is going to be able to give more what's it? It's going to be able to give more electrons, so it's going to be a stronger donating group. And because of that, that is going to make this 2 and this one 3 and this one, no wait, 2, 1, 3. Right, 2, 1, 3. Because the stronger donating group is going to cause the minus charge to increase, right? The minus charge is going to get bigger. The weaker donating group is at a smaller rate, and the electron withdrawing group that's strongest is just going to be pulling electron density, which is going to make the minus charge smaller, making it more stable. Does that make sense to everybody now? Sorry about that. Please forget the first time I did the problem. My bad. Any questions on it? Like, I can clarify anything. Yeah. Number 3. Okay, so number 3. We're looking at the okay, so the amount of hydrate form is essentially just asking what is the most reactive. So let's just look at it like that, right? So the most reactive one is going to have the highest partially positive charge, right? Because that's going to make it more unstable. So if we look at this, we have an electron withdrawing group by, let's call this just by induction, because by saying by resonance and induction, it makes it seem stronger than it is, by induction, right? And then we have an electron withdrawing group by resonance. Then we have an electron donating group, right? So an electron donating group is going to make that partially positive charge decrease, right? This electron withdrawing group by resonance is going to cause that partially positive charge to increase because it's going to pull even more electron density, right? So this is going to increase a lot. And then this one is going to be an electron withdrawing group by induction. So by resonance and by induction, the electron withdrawing group by resonance is going to be a lot stronger than the one by induction, right? So even though it's going to pull some electron density to increase the partially to increase it, it's not going to be as much as the one by resonance, right? So because of that, we put the numbers 2, 3, and 1, because this is going to have the highest partially positive charge, and this is going to have the lowest partially positive charge. Does that make sense? All right. Yeah. Ketone is more withdrawing than that ester. Yeah, I would say so then. Not really sure the rankings about like which one is the strongest withdrawing groups, but according to this, yeah, the ketone would be more withdrawing. I don't know about any like actual official. Yeah, just based on this, yeah. Yeah. I'm sure if it's based off this, it'll be in real life too, but I don't want to like give a concrete answer. Oh, okay. Any other questions? All right. And on number 5, no questions too? Alpha beta. Okay. Perfect. All right. On to the reactions. So starting off, we have a carboxylic acid treated with ClCl2. Right? So ClCl2, I'm pretty sure we learned this. This was last exam. We learned this last exam, and what it did was it turns this OH into a Cl, right? It becomes the acyl halide or the acid halide. So our first step have the same amount of carbons, double bond O, and then this becomes ACl, right? And then we have our group adding on. Forgot what the name of this reaction was, but even though it's 2 equivalents, we're only ever going to add 1 to it. It had like a really nice name, but I forgot it. So what this is going to do is going to take care of the Cl, and then it's going to turn it into, or it's just going to add this entire group onto it, the CH2 benzene group, instead of that Cl. So what that'll look like is like this. Sorry. And then like this, instead of that, we have our CH2 bonded to the benzene group. And then lastly, this is a Wittig reaction. Wittig. I don't know. I'm not sure if I'm pronouncing it right. Anyways, so what that does, it just takes the place of this oxygen, right? So this oxygen is no longer going to be there. Let's just assume that this is the oxygen now, right? So this oxygen instead has or there's no oxygen in there anymore. Instead, this carbon has the double bond to the CH, right? So what that looks like is just this. Okay, and then I'll add the CH2 with the double bond first. CH2 with that is not a CH2, right? And then now we have to put our CH in the benzene group right here. So this is going to be our CH bonded to our benzene group. Actually, because it's a double bond, we actually do need to show a little bit of stereochemistry because in the Wittig reaction, the big groups are trans to each other. So C, in this case, we'll put H right here, and then we'll put our. So yeah, they're pretty strict about that. So don't put this benzene onto the other side with just don't put it on the same side as the other benzene, right? Any questions on this first reaction? Sounds good. All right. So next one. So there are two kinds of reactions that we can get with this that are fill in the blank, right? So we have the geminal diols, and then we have Stork synthesis. So this is going to be Stork synthesis, and we can tell because this double bond it becomes a double bond again. It becomes a carboxyl again, right? Because in with the geminal diol, what happens is that not that in the geminal diol, but what am I trying to say? I get what we have a geminal diol question. As soon as we get to it, I'm sure I can remember. So this is Stork synthesis, right? So in Stork synthesis, what we want is first step, we're gonna have a secondary amine. And then second step, we're gonna add the group that is meant to be added. And then third step is gonna be H3O plus. All right. Very easy to remember. We just do it and you forget about it. So the secondary amine. So you can use any secondary amine. You can use the N like this, and then just say NH like that. Or what usually ends up happening is I think this is a given one. So if you do use it, maybe I guess props, right? So you use that NH like this, and this is considered a secondary amine, right? So what this does, it's very similar to the geminal diol. So it acts as like a protecting agent, I guess. So this aldehyde comes our nitrogen is attached this, and now we have that. And so now our second step is we have to add this sorry, I should finish this. So the first step, essentially what we've done is we made this carboxyl into this secondary amine, right, into a tertiary amine, right? This nitrogen has 3 bonds to it. So it becomes a tertiary amine. Our second step in this problem is that we are going to missing something. I can feel that I'm missing something. No. This is, yeah, I'm missing the double bond. That's exactly what it is. Thank you. I really appreciate that. We have the H plus, right? And this is gonna be, yeah, this is gonna be in acidic conditions, right? So we have the double bond, and now we need the this group to come and attack. And this group isn't just gonna come and attack like normally, right? It needs that double bond to be there for it to attack, for it to be attacked, I guess. And so what that's gonna mean is that we're gonna put our group, right? 3 dash CH. Let's just think of it as an SN2 reaction, maybe. CH double bond CH double bond to CH2. and then we'll put a bromine at the end. And what this will do is that this double bond is going to come and attack this carbon right here, and it's going to create just the minus charge right here, or I guess it happens. I think it happens in one step. I'm not sure, but with the H3O, but what we are gonna have, no, it's not gonna happen in one step. So two, what we are gonna have is that this double bond is gonna come and attack this CH2, right? And then this Br is gonna leave. And then this double bond, what's gonna happen to this other is gonna create this double bond, is gonna create an imine. So we have our imine with our nitrogen with a plus charge now, right? That's gonna be product of our second step. So, wow, that is bad. All right, so now we have our imine. That the same amount of carbons? Yeah. Okay. So now we have our amine plus charge, and then we have our this group, and then we have the group that we've just added, CH2-CH, double bond CH, CH3. So now that we've added our group, now we can just use H3O, and H3O gets this nitrogen off, and it recreates this aldehyde right here, right? And so the product of our third step is the final product that we have in the problem. Any questions? Yeah. No. Okay, so in the first steps, yeah, sorry. In the first step, this nitrogen comes and attacks the carbon. Oh. No, no, okay, so the double bond is the one that it's attacking, right? So this is a partially positive carbon right here. So this double bond, the electrons that are in this double bond are going to come and attack this partially positive carbon right here, not the double bond carbon. So these are the double bond carbons, and it's not attacking this. Oh, so in Stork synthesis, you have and the amine, it becomes an imine. Like the goes from amine to imine. Yeah, there is going to be a double bond on the nitrogen whenever we have Stork synthesis. No, no, the plus charges don't attack this. Where's the plus charge? Uh, it's just the protonation. Yeah, just getting rid of the. Yeah. Oh, are you talking about this arrow? Oh, okay, okay, no, no. This arrow was essentially just saying that the nitrogen was leaving. One more time. That was just the mechanism that I was just trying to explain. So this double bond is gonna come and attack this one, right? But then the what's it? This there's gonna be some electron density, or no, sorry, yeah, the arrow is completely wrong. You're right. Yeah, the nitrogen, yeah, the lone pair of the nitrogen is gonna come and stabilize that. Sorry about that. I really appreciate it. Yeah, that was the wrong arrow by me. Did that clear it up? My bad about that. All right. Any other questions? Yeah, any secondary amine. If you just use and then dimethyl, that'd be fine. Okay. So next problem. So this we are doing a cleavage type reaction. So CH3NH2, this is a primary amine. Whenever we have a primary amine that's going to be reacting with an ester, what it's going to do is actually it's going to cleave this bond. Or I mean, technically, you don't have to show which one it cleaves because both this is a cyclic compound. But yeah, so it would cleave any one of these bonds, but it will only cleave one. Okay, so I'll cleave this bottom one. And so what it's going to do is that it's going to add this amine right over here, and it's going to create an amide. So ester to amide, right? So the product of this reaction is that we're going to have, this is how many carbons? 1, 2, 3, 4, 5. Just like this, we'll have, so on carbon 1 and carbon 5. So on carbon 5, we're going to have our yeah, amide. So this is going to be N, or yeah, NH2CH3. H2 has NH, yeah, NHCH3. CH3, so it has no charge. And then on the left side, it's going to have an O minus charge. So it hasn't been protonated yet, right? So that's going to be our product for step 1. So now step 2, CH3OH and H plus. What this is going to do is Fischer esterification. So Fischer esterification. So we're essentially, we broke this ester and created an, technically this is a carboxylic acid, right? And so this carboxylic acid is going to react with the CH3OH and H to produce an ester. So it's going to do carb acid to ester. So what that's going to look like, wow, that was bad. This is NHCH3 still, and now we have our ester. Remember, for Fischer esterification, we're adding this compound here. If it's like 10 carbons long, then we're adding 10 carbons. If it's 1 carbon long, we're adding 1 carbon. So we have our CH3O. So this is going to be our O, and then we'll add our CH3 right there. And our last step, step 3, LiAlH4 and H3O plus. So this is a strong reducing agent. And what it's going to do with esters and amides, esters are going to go all the way back to an alcohol, and amides are going to go all the way back to amines. All right. So in this case, we're going to have a primary amine, or not a primary amine. I guess it's a secondary amine because it has the CH3 attached to it. So it'd be a secondary amine, but it would essentially just get rid of all of the carboxyl groups, right? So these carboxyl groups are gone. So we have our 5 carbon. On 1 carbon, we have the OH, and on the other carbon, we have our NHCH3. And that is our final product. Any questions on this reaction? How I got there? Yeah.
Completely related to this, but what that do compared to the LiAlH4? What would that reduce?
Wolff-Kishner. So if we, I don't think we would, Wolff-Kishner would do anything. Yeah, I don't think it would. Would it do anything here?
I'm not saying it would do anything here. I just, since you noted what the thing was does, like what would the other Yes, what else?
react. Oh. We just cut it off right here. Yeah.
The ester, I don't think it'd do anything with the ester. I think it's specific.
Okay.
So, no, so on the right side,
Uh-huh.
so you literally just link that carbonyl connected to that B,
That
bring it by one. So you have the ester, CH2, 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 and HCH3.
oh, okay. Any other questions on that? All right. Next problem. NH3 and then the heat, I guess. We have a carboxylic acid here. C, right? And so our first step, NH3 with heat, this is going to be our carboxylic acid, and this is going to create an amide, right? So essentially, it's kind of like Fischer esterification. It's just that instead of creating an ester, you're going to create an amide. So same thing happens. So first step, out of benzene. We're going to have our C double bond O and then an H3. That is our, I guess, NH2. Right, lone pair. SOCl2 in this case. So remember with carboxylic acids, what SOCl2 does, it creates the acid halide. In this case, the SOCl2 is going to create not cyanide. Yeah, cyanide. It's going to create cyanide, which is C triple bond end. So the nitrile group. So first step was this. Second step, so this carbonyl is gonna go away and is gonna create a triple bond with this carbon right there and get rid of these hydrogens. So product of step 2, no, not a benzene. C triple bond N, right? Lone pair if you want. And then next step, LiAlH4H2O. So this is going to reduce our nitrile and it's going to reduce it all the way down to an amine, right? This is a strong reducing. So we'll reduce it all the way down to an amine. And remember the amine is like our single bond to the nitrogen. So same thing happens. We have our C and that's going to be bonded to NH2. So this is going to be a CH2. Yeah. So CH2 bonded to NH2. And then lastly, we have a ketone in acidic conditions. This is going to it's going to create the imine. Sorry. This is going to create the imine. So the way it's going to work is essentially this NH2 is going to get this double bond attached to it. So instead of having an NH2, it'll be like this cyclo, the CH2 bonded to a nitrogen. And this nitrogen is going to take the place of this carbonyl group. So we'll have our double bond bonded to carbon, bonded to carbon, and then two methyl groups bonded, 3CH. And that will be our product we have in imine. All right. Any questions on that? What you got there? Yeah. Whenever we're doing stork, the nitrogen replaces the oxygen. Wait, what do you mean? Uh-huh. Mm-hmm. Yeah, it's gonna be with H3O plus, yeah. So this isn't stork synthesis. This last final. It's the primary amine with the it was the same thing like this. The primary amine with the what's it with the carboxylic acid, right? Or the ester. It was essentially the same thing. Okay. All right. So this one we're gonna be using our Gemino dial. So because of that, okay. So our first step in these problems is always going to be used to use the Gemino dial. So gem dial / H plus, right? Our second step, we're going to be adding the group right here, right? So whatever group we're going to be adding is, so in this case, it's going to be our cyanide. So we're going to do our add group. And then third step, H3O plus. All right. So the same thing happens with all of the Gemino dials, right? So whenever you have a Gemino dial, it's going to be acting as a protector for certain groups. So in this case, we wanted to protect the aldehyde, right? So let's do that. So whenever we have the Gemino dial, we'll use our OH like this. So what that's going to do is this, like that. So it's like that. Then the is going to be right. So now we have two protected groups, and not two protected groups. I don't know why I'm protecting this one. Our ketone is not going to be protected. Now we're going to add our group, and so this is going to be using just HCN, right? And so what HCN is going to do, our second step, we're going to have this. This group is still protected, right? But now our CN is attached here, and we have an O minus. And finally, final step, H3O plus, it's going to protonate that O minus to carry an OH. And then it's going to bring this protected aldehyde back to its state as an aldehyde, right? Any questions on that problem?
The,
Hmm?
the 7%.
Yeah, NaCN, yeah, that's fine. Any other questions? Yeah, the thing is with NaCN, you have to do it in acidic conditions. So just make sure that you write the /H plus. Yeah, /H plus.
I guess, yeah.
Yeah. If you what? If I didn't have the H plus. If I didn't have the H plus, the reaction wouldn't be able to the geminal halide would or geminal diol would not be able to react with the aldehyde. Yeah. This is HCN. You can also use. Sorry, I should probably write that out. Sorry. NaCN/H plus. Yeah, if you do NaCN, you have to use H plus. Otherwise, yeah. Otherwise, I would just use HCN. It just makes it a little bit simpler. Any other questions? All right. So final problem. All right. So in this problem, we have the beta keto ester. So in this, the first step, NaOET, ETOH, ethanol. So what this is going to do is this is going to deprotonate the most acidic hydrogen. So the most acidic hydrogen is going to be right in the center. And usually whenever you see the this sodium OET ethanol, this is gonna pretty much always just deprotonate this middle carbon. All right. So first step, it's not gonna change the structure at all. So we'll still use the same thing that we have. Oh, it's just that now we have a minus charge on this middle carbon. Now we have kind of an SN2 kind of like reaction where we add this CH2Br. And what that's gonna look like is just this minus charge attacking the carbon that's attached to the bromine. So it's gonna connect right at that point. So what that's gonna look like, step 2, we'll have our this double bond, then that's first. This is attached to CH2. How am I doing on time? 10:15. Okay, be good. All right. So now that we have that, this third step, H3O and 180 degrees Celsius. Uh, so in this one, we're gonna have it cleave the ester off, right? So we have the beta keto ester. And so now what H3O and 180 degrees Celsius is gonna do in this situation is it's gonna cleave this ester and just cause it to be this ketone with the CH2 benzene ring attached to it. And this ester is just gonna go away. So that'll look like in the final product. Is the CH2 now, and then just like that. All right. Any questions on that? No problem. Yeah. Yeah, the ester is gonna be the one that's leaving. Oh, and this one you do? I did not know that. I don't think so. Okay, well, either way, yeah. If I'm not sure if you do need to, but if you do need to, then it's good to show it anyway. Um, the most stable is gonna be whenever, let's say this goes over here, and then this is a minus charge now. So oxygen is the most electronegative atom, and with whenever oxygen has that minus charge, it's gonna be having a full octet, right? So we'll have our O minus like this. Single bond, O minus. Um, and this will be right here. And then we also have it going the other way, right? So that O minus has, that oxygen has the minus charge. And I'll just show that like this. Sorry, it'll look a little cramped here, but I'm just drawing resonance structures, so. O minus O, that, and that will be the other resonance structures that you would have to draw then. Um, I don't think it's necessary to draw both because both of them are stable, right? I don't think there's I guess in this case the most stable would be like this one because it has some resonance onto that side. The whenever we have this top one, because this minus charge. Oh, actually, I can't even do that. Yeah, then I mean I think both of them are fine. Either resonance structure. Um, any questions? All right. No questions? All right. So mechanism. So the mechanisms is quite long in this chapter. But they're pretty simple. They kind of just go they go with the flow, I guess you could say, right? All right. So the first step for this mechanism, we have a Grignard reagent with the cyanide. So our first step, and you guys are gonna have to bear with me a little bit. Uh, this triple bond is gonna come and attack this carbon right here. And what that's gonna cause is or like some electrons from that triple bond, it's gonna cause an imine to form, right? So we have our N like this, uh this N. Wait, let's focus on this. CH2, CH3, and then this N is gonna have a two lone pairs, so have a minus charge. Then the MgBr is going to be our plus charge, right? So this is what we're going to start off with. Right, so this will go this way. And now let's just use our second step. We have an H3O. So this oxygen has a plus charge on it. This nitrogen has a lone pair that it's willing to attack with. So this lone pair is going to come and attack this hydrogen to form a covalent bond with it, rather than having this ionic interaction. So what that's going to do is C2CH3 bonded to NH. And so now there is no charge on the molecule. And then it's going to do it again. So this NH has a lone pair, H-OH2 is a plus charge. It's going to come and attack another hydrogen. So now whatever we're going to have, we have this C single bond CH2, CH3, and then our double bond to an NH2. And this is going to have a plus charge. Now, okay. Now this because these OH2s have been deprotonated, we can use H2O as well. So H2O comes and attacks this carbon, right? So it's gonna attack this carbon, create a bond with it, and then also kick off that NH2, or kick off that bond to create the to uh, to stabilize the positive charge on the NH2, right? It seems like it is a lot of steps, but it's kind of just how the mechanism goes, right? This is just CH3 NH2, right? And now there's no charge there. Now we have an OH plus charge. What we can do now is we can deprotonate the oxygen, H2O, and snag that. And now our oxygen has no charge on it. So again, we'll redraw. H2, CH3, H2, and now we have our OH. Okay, and one last time, this NH really wants another hydrogen, so it's gonna get HOH2, and with this plus charge, this nitrogen is gonna come and attack this hydrogen, break off this bond. And so our next step, we're gonna have an NH3 with a plus charge. What? Mm-hmm. Well, yeah, I mean, it's easier to take it from the H3O plus is the thing, right? So if it can take it from the water, like theoretically, but I mean, if you have the ability to use H3O plus, it's gonna go for the less energy. Yeah. And H3, and now we have a plus charge there. And finally, we have our NH3 leaving. So our oxygen has two lone pairs that it can use to resonate in order to get rid of this charge, right? Or not get rid of the charge, but remove the charge. So one of these lone pairs can come and create a double bond with the carbon and cause this NH3 to leave. And if you notice in the problem, we have to have our NH3 leave. So because of this resonance, we have our C double bond O H with a plus charge, and then our plus NH3, and then we have our CH2CH3, right? And one thing we do need to do with this problem is that we do need to show all resonance contributors, right? So we'll go like this, draw our double arrow, and this double bond can come and stabilize this oxygen to cause it to have a minus, a no charge, and then the carbon to have a plus charge on it. So what that'll look like is like this, carbon with a plus charge, CH2, CH3, then our OH, sitting pretty with no charge, right? So that's me do it with this, right? So this is all a what's it? The resonance structures, right? So these are all the resonance structures that we have. And now what we can do, our final step is that we need to get this we need to get a ketone right here, right? So what we can do is just we can deprotonate this oxygen using H2O. So that H2O, the oxygen can come and take that hydrogen and then break this bond with the oxygen. And we have our final step, which is just our carbonyl, the double bond on the oxygen plus CH2CH3. And that is our other product right here. And our NH3 has been created already right there. All right. So that is the mechanism. Any questions on that? How I got that answer? Any questions? All right. Solid. Synthesis. Very fun. So synthesis, we have a tertiary amine. One thing about synthesis is that in this year, it is very, very repetitive, I guess. You'll do things and then you'll do them again, and then you'll have to do them again. So you guys will understand what I'm talking about once we get to this one. So we have a tertiary amine. The first thing we want to do to get rid of this, to break this compound down, is we want it to become something that we can work with. And something that we can work with is an amide, right? So one way that we can get an amide is LiAlH4 and H3O, right? Or not H3O. In this one is LiLH4 and H2O. Sorry about that. So LiLH4 and H2O, what that'll do is that that'll create a an amide with the oxygen right there, right? So remember in synthesis we are working backwards. So sorry, I should have even checked for, sorry about this. We want alcohols or alkenes of 2 carbons or less and benzene. All right. So we'll try to get this benzene away from each other, and then alcohols or alkenes, we'll try to get these amides into an alcohol, or an amine into an alcohol. So we'll start with this. So we have a CH2C, which is bonded to an oxygen, which is bonded to an the amide. So this is our amide. And so now our next step is going to be to get rid of the amide, right? So what we can do, you just cleave it down the middle. And what this will cause is it'll make it become the amide with the acid chloride, right? So we have our benzene, CH2 bonded to a carbon double bond oxygen, O, not O, Cl, because we want the acid chloride, plus our secondary amine. and this is have an NH. Okay, so we'll start at the secondary amine side. So one thing we notice is that secondary amine and tertiary amine, both of these can go through the same reactions. So one thing we can just do here, LiLH4H2O. H2O. So this NH is going to have one that's going to be an oxygen to make it an amide, and the other one just chilling like that. And we can just do the same thing again, right? So this oxygen is going to be an acid chloride, Cl, and then it has one carbon off, plus our NH that has that has two carbons onto it, right? And so what we can do here is we can SOCl2. This will create our carboxylic acid, and then we can use Jones to use a primary alcohol. Sorry. We'll start. We'll do on that. Oh yeah, NH2. Yeah. Sorry about that. So whenever we do that, then now we have NH2, and this is a primary amine, and we can just do the same thing. This LiAlH4 slash, not slash, 1, 2, H2O, and that'll do our NH2. We'll have our amide back, not amide. Same thing, cleaves it off. We have our acid chloride, and we've already done this, so we can just draw the arrow back like this, because these are both the same structures, and we have plus NH3, which is fun, right? Okay, and onto the left side. So we've done everything that we need to do over here. We've made our acid chlorides, all of this, all good and dandy. Left side. Now, same thing. We have our acid chloride. And what we can do here is that we can create it, make it back into a carboxylic acid. We can do that using SOCl2. So what this is going to do, I think you can also use CuCl2, right? CuCl2. I think they both do the same thing. CuCl2. So either or. So what happens here is it just creates the acid halide. So now instead of our acid halide, it creates the acid halide from a carboxylic acid. You have our carboxylic acid, and now same thing. We can use Jones one more time. CH2 C H CH2OH, right? And so now we have a primary alcohol, and what we could do is we can use Grignard twice, right? We can do, like, for example, we can cut this off with Grignard, and then we can have this one have the MGBR, go back, and then use PBr3, get that become an alcohol, and then cut it off over here. Or instead, to make it easier on ourselves, we can just go and cleave it from the very beginning, right here, and we can say then H3O. They're still using Grignard, but we're using a different kind of Grignard. So we would have this with the MGBR, and now that is going to be attacking the epoxide, right? So we're back to epoxides, and epoxides we know MCPBA, BA, and we have our double bond, and that's CH2 double bond CH2, right? So that's good. And then on the left side, MGBR, we can get rid Mg slash ether. And then we have the Br still. Then we can use Br2 FeBr3. That will leave us with the benzene. Any questions on that? Um, Anyone want me to do it the other Grignard way, the longer way? No. I think everyone's ready to leave. All right. So we are finally on to the best part, spectroscopy. All right. So to start our puzzle, we have C7H12O2. So C7, we're gonna use the unsaturation number first. So 14. So two. Sorry, I should write it down. 2C minus H plus 2 plus N. Very important. I think you guys might have N's on the final, right? This exam or next exam. So please be careful with your nitrogens. Hopefully, nitrogens are pretty easy to tell because they will usually have the very broad peak over here. So, um, just know, right? And it'll also tell you that it has a nitrogen. So all of that divided by 2. So yeah. So right now we don't have a nitrogen in ours. So that's very nice. So 14 minus 12 plus 2, all divided by 2. 14 minus 12 is 2 plus 2 is 2, or 4 divided by 2 is equal to 2. All right. So we have an unsaturation number of 2, and that means we have either a triple bond or we have 2 double bonds. All right. So it's either or. So now let's look into this. Wow, that looks annoying. Okay. So we'll start. I'll skip the spectroscopy for now. And we'll start with the proton NMR. So first thing, we have a CH3 bonded to 1, 2, 3 that is bonded to a CH2 group. All right, and it's very, very close over here, which means it's not close to anything that's any of the oxygens that we have. Right, so it's not close to any of the oxygens. So we'll keep that in mind. Then we have this CH2, which is bonded to 1, 2, 3, 4, 5, 6. How does that happen? All right, we'll skip that for now. That's a little bit annoying. All right, let's skip that one for now. The next one, CH2. This CH2 is bonded to 1, 2, 3, 4, 5. That makes a lot more sense. So, right? So minus 1. So that means it has CH2s on either side. Right? So let's just like this. Or I guess 2 box that. Right? All right. And so now we have our CH2. This is bonded to another CH2. So CH2 bonded to CH2. And this is quite downfield. So maybe on the other side, yeah, 4. Maybe on the other side, we have just straight connected to an oxygen, right? So we've accounted for a lot of carbons, and now we have 3 more, right? So in this range from 6 to 7, this is our alkene peaks. What this means is that we have an alkene. All right, so we know what one of our double bonds is accounted for, so it's not an alkyne, so we'll get rid of that. And one of our double bonds is going to be alkene. All right, we have yet to find out what the other double bond is. So if we just looked at the alkene, we'll just draw their carbons. So if we look at the first hydrogen, so one hydrogen, this is going to have a hydrogen on just one area attached to it. So let's just name a random hydrogen. Okay. And now on the other side, or on the same side, we'll have a hydrogen. So I'll just write it on the same side. So it'll be either or. So it'll either be this hydrogen like this or this hydrogen like this. Either way, as long as we do it step by step, we'll get the correct answer. So I'll just do it like this. And I'll also do it the other way just to show you guys. The next hydrogen, uh, this hydrogen is connected to 1, 2, it has 4 peaks, which means it comes into Oh, that's a little bit weird. Okay, let's not even worry about that. The next one, we know how to do this. This hydrogen is gonna have one hydrogen in its plane. So let's just put that right here. So this hydrogen is going to have one hydrogen in its plane, and so then that means this is going to be bonded to something with zero hydrogens, right? And if we look at it this way, this hydrogen is bonded to this hydrogen, which is in the same plane as this one, which makes sense. Then this hydrogen, which is also in the same plane as this one. So because of that, we have our 1 plus 1. I don't know why it's 4 peaks. Maybe I'm just miscounting. But it makes enough sense for me to be pretty confident on it. And then we have our first hydrogen right here that's bonded to another hydrogen like this. And then on the other side, same thing happens just to get one hydrogen. So we have the CH2 on either end, and one of them has the no or no hydrogens attached to whatever that is, right? So now let's see if we can put it together. Actually, I like to look at the carbon-13 NMR just in case. So we have two oxygens here. So if we look at the carbon-13 NMR, if we have two oxygens, we could have carboxylic acids and esters, right? So that's at carbon-13 of 160 to 185. And if we look here, yeah, we have one exactly at around 165, right? So we could have an ester or carboxylic acid. So we could have an ester or a carboxylic acid. Let's see if we have a carboxylic acid, right? So let's look through here. OH stretching for carboxylic acids. 25 to 3000, it's going to be a broad V shape. Excuse me. So 25 to 3000, we do not have any broad V shape, right? So because of that, we know it's not a carboxylic acid, it's an ester, right? So we have an ester. So our second double bond right here is going to be part of an ester. And now we know that this oxygen that's right here, connected to these two, is going to be part of the ester chain, which is always going to look like that. And we have one carbon right here, right? And so if we continue crafting, if we look on this side, this alkene, we have one with no carbons attached to it, right? On the right side, we're not going to get that probably because it's so downfield or it's so upfield that it's not even like it's not close to the carbon or the ester at all because it's so upfield. Like this CH3, CH2, all of these are very upfield. Like look at this, it's at 1.8. So this is probably on the right side where it's going to be more upfield versus on this side, right? This is going to be more downfield area of the problem. So this could be this carbon that's bonded to this double bond O bonded to that, right? So if we put it like this, if we just attached it, we have our carbon attached to a carbon with the double bond H and CH2. And so now we've taken account of 3 carbons out of 7. And this CH2, CH2, and we only have CH2s and CH3s. And so because of that, we can just continue CH2-CH3. And perhaps that makes this carbon make sense now, because this one is going to be probably this CH2 or 8. It should have 8. I don't know why it's 6. It's really weird. Yeah, maybe it is overlap. Yeah, that might be it. Either way. So now we have an ester with the terminal alkene. So if we just, let's draw it out real quick right here. CH2, CH bonded to carbon, O1 with O, ester, CH2, 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 CH3. So we have our 7 carbons, our 2 oxygens. We have our 2 double bonds, so that means all of our hydrogens are fine. And now, one thing we can also do to check is we can check if this is actually a terminal alkyne or alkene. If we look maybe over here, We have alkenyl stretching. This is the terminal alkene. Oh, okay. 985 to 1000. That's fingerprint range. But it has one at 985. So maybe. Maybe if there's something on the carbon 13 NMR. Or not the, I mean, yeah, the carbon 13 NMR. Exactly. So alkene, okay. That is, okay, yeah. 100 to 170. It's kind of a big range. But if we look, yeah, we have two carbon peaks there, which means we have two carbons part of the alkene. It doesn't really tell us that it's in terminal, except that we have this fingerprinting region that tells us it's terminal. But otherwise, yeah, it seems that everything checks out here. Our CH3 is bonded to that CH2, and these are very, you know, um, far from the deshielding atoms right here. This is slightly deshielded on this side, which makes sense for over here. And then this over here, very deshielded CH2 that's bonded to the other CH2. So that is going to be our answer for the spectroscopy. Any questions on that at all? Exam review for the final is next Monday and Tuesday.
believe so. I think so.
Final date of the
Tight.
I decided that like if we just do it at the regular